section of our notes. We are going to look at something called solvation, and we're going to look at how do we make a solution faster or how do we make a solution slower. So in order to start us off, instead of me talking at you, I've got my friend Tyler here. He's not really my friend. He's got a great channel on YouTube. If you've ever seen him, it's Tyler DeWitt Chemistry. But he explains solvation in a way with the manipulatives in the video that is far more than what I can do even with my document camera. So we're going to listen to Tyler. I'm actually going to scoot it ahead just a little bit in the video, and he's going to show you the solvation process with an ionic compound and then a covalent compound. And then from there, we're going to talk about how we can affect solvation or that dissolving process, and we can speed it up and we can slow it down. So with the video that we have here,
What happens when stuff dissolves? I mean, like, what happens to...
So we're going to, like I said, we're going to speed it up just a little bit. Right now, what he is doing is he's talking about the fact that we have ionic compounds and we have covalent compounds. Ionic compounds are things like table salt, which are made up of sodium ions and chloride ions. And then we have our covalent compounds, which are made up of individual molecules. So
an ionic compound, this grain of salt over here. Anyway, let's look at what would happen when we dissolve these. We'll take a grain of salt, dip it in the water, and start stirring around. With our atomic vision.
So you can see here that the red particles are the sodium ions, the blue ones are the chlorine ions, and right now they're all stuck together and he's got one little chunk of salt, one little grain of salt. This is sugar. It's made up of carbon, it's made up of hydrogen, and then it's made up of oxygen. And this is one little chunk or one little molecule of sugar, which he is saying is C2H4O2, just to simplify that sugar down.
We're going to see that the atoms that make up this salt are going to come apart from each other. They're going to break apart, and they're all going to start floating around in the water individually. This is what it looks like when salt dissolves. Okay? Now let's take our sugar. Here's our grain of sugar. It goes in the water, we stir it around, and the grain of sugar is going to break up like we saw the grain of salt break up, but it's going to break up in a different way. It's going to break up into the individual molecules that made it up. But these molecules are not going to break up into the individual atoms. They're going to stay as molecules, and those molecules are going to start floating around in the water. A big mistake that people make, I don't want you to make this mistake, is they think that when sugar or other covalent compounds dissolve, they think that the atoms that make up the molecules totally break apart. And then you end up with a glass of water that has all these carbon and oxygen and hydrogen atoms just floating around. That does not happen. Big red X. Instead, the molecules stay together. Well, the atoms in the molecules stay together. So this is a big difference between how covalent compounds dissolve, where the molecules stay molecules, and how ionic compounds dissolve, where the grains of these things like salt actually break apart into the individual atoms.
Okay, so that's actually where I'm going to stop that video from Tyler. The whole video, if you want to watch it, is pretty decent, but again, I kind of gave you the synopsis of it before and right now. But the big thing to look at with these is with your little bitty chunks that we have here of the salt or with the sugar. The solvent is going to hit what these are, the solute. And the solvent, when it bombards it, that's what actually breaks away the pieces and it pulls it into the solution. So it's not like these things are just willy-nilly breaking apart on its own. It's the fact that the solvent hits the solute and it pulls the little pieces. Remember, water's weird. With water being weird, it is polar, it has hydrogen bonds, so it doesn't break itself apart. But with it being polar, it's able to pull apart those little ions that are in the solution. And when it pulls apart the little ions in the solution, that's what breaks it down into those ionic little ions, the positive and the negative charges. That's why they conduct electricity. These do not conduct electricity because they stay whole little molecules running around in the solution. But the same thing happens if you've got a big, huge chunk of sugar. The solvent hits the solute, it pulls one of those little molecules away. Solvent hits the solute, pulls a little molecule away, and it pulls it into the solution all over. So when we are trying to dissolve things, we can affect the speed that actually happens. When it affects the speed that it actually happens, we either have the heat, meaning how fast the particles are moving or how slow the particles are moving. You have the surface area, how much of that area hits the outside, that the solvent can actually tap the outside of that solute. And then we have stirring, which means that you are moving the particles around. So when you are looking at the surface area, again, the outside pieces, like around the outside, or this, you're actually seeing this middle part here, that's touching the outside. So the smaller the piece, the more surface that actually touches the solvent. The more frequently that you can get the solvent to hit the solute, the faster it's going to break apart. So when we have smaller and smaller and smaller pieces, more of the solvent is hitting the solute and it's breaking down. So when you increase the surface area, you're making the particles smaller. So the more surface that touches the solvent, the faster it's going to break apart. So if you want something to dissolve very, very, very slowly, you're going to use a big, huge chunk. But if you want something to break down very quickly, you're going to powder it down and you're going to make those particles as small as you can because you're doing the work for the solvent, breaking it apart. So when you're increasing the surface area, you're crushing it down. Like I said, you're making it like into a powder. If you want to decrease the surface area, you're pulling the pieces together. So changing the surface area, you're either crushing it or you're leaving it large. When you crush it up into smaller pieces, you are increasing the surface area. When you are leaving it large, you're decreasing the surface area. So when you look at the next factor, sorry, I was catching up with this slide. When you are looking at the next factor, it is stirring. So again, the more frequently that you can get the solvent to hit the solute, the faster it's going to break apart. So when you stir something, you're making the particles move around in the solution. And as you make the particles move around in the solution, you're increasing the frequency that the solvent hits the solute. Therefore, it's going to break apart faster. So if you just take, sugar and you put it into water, it's going to dissolve because all those particles naturally move, but they're not hitting as frequently. So because they're not hitting as frequently, it might take a really, really, really long time for it to dissolve. So if we wanted to speed that up, we would stir it around or shake it or something like that, and that's going to increase that frequency. But if we want it to go very slowly, we're just going to dump it in, let it sit, and it will break apart very slowly. So as you are looking at the dissolving factor, stirring does have a big effect on that as well. So again, the more frequently that you can get these little solvent particles, like the water molecules, to hit the solute, which is table salt in this case, the faster that you can actually get it to break apart. And then right along with that, heat has an effect on the molecules as well, because when you increase the temperature, the particles move around faster. So if they're moving around faster with a bigger force, the solvent is going to hit the solute more frequently. When the solvent hits the solute more frequently, it's going to collide and it's going to break those things apart faster. So the three things that affect your speed of dissolving, your solvation, is going to be stirring, changing the surface area, and by your stirring, surface area, temperature. I couldn't remember the last one that I forgot to say. Now looking at this, we've got two more words to define real quick, and then we're done with this section. The last two words that we're going to define is the fact that when things break apart, so the solvent hits the solute, it breaks it down into the different little pieces. When you're breaking it down, you either have an exothermic process or you have an endothermic process. Your exothermic process is releasing heat. So when the little particles break apart, that extra heat goes into the environment. Remember, heat only travels from hot to cold. So with that heat traveling from hot to cold, it's releasing its energy, going to you, making you feel warmer. The opposite effect of that is the fact that when you have those little particles stuck together, the solvent hits the solute. When the solvent hits the solute, it's going to bombard it. Those little particles are going to break apart. When those little particles break apart, it's going to feel cold because it's absorbing your energy. So with an exothermic process, heat is exiting from the process. Endothermic, heat enters into the process. That's actually as far in the notes as we needed to get in this section. If you guys have any questions, make sure that you ask. Otherwise, have a great day.